So last lecture that we have on this unit and for the year is over molarity, and molarity is just a unit for concentration. So lots of times in chemistry what we want to do is we want to take these compounds and we toss them into water and we want to dissolve them. And in the process of doing that, we get something known as a solution. We talked about that in the second unit, which is just a homogeneous mixture. So that's what a solution is. We want to break this down further and be able to identify what part is the solute and what part is the solvent. So this is a good day for hot chocolate. So let's draw a big mug of hot chocolate. And here we've got some milk. It's the good stuff, not that water. And then here, that looks tasty. There's a big old chunk of chocolate. So if we had something like this, then we would say that the milk is in larger amounts and it's doing the dissolving. So that would be known as the solvent. And then the chocolate is in smaller amounts and it's being dissolved. So that is going to be the solute. Just like solvent is a bigger word, it's in bigger amounts. Solute is a smaller word, it's going to be in smaller amounts. So this whole entire thing is known as the solution. So it's good for us to think about those parts of that solution when we try and identify these things. Molarity is just looking at the concentration of that solution. It's a way of describing that. So you can have something that's very concentrated or much less concentrated, more dilute. So if you have a whole bunch of your solute, well, if you have a bunch of solute, then it's going to be more concentrated. If you have less of your solute, it's going to be more dilute or weaker. And the example that's talked about here is coffee. Okay, our formula that we're going to be using. So in chemistry, we're not going to be talking about concentration as parts per million or anything so much. It's going to be as molarity. And you guys have already done some labs where you've done labs with 0.1 molar hydrochloric acid or 6 molar hydrochloric acid. 6 molar hydrochloric acid is the stuff that makes me a little concerned, and I get all nervous back there because that's much more concentrated. So molarity, and by the way, get into the habit of writing a big capital M because later on we're going to come back with molality, which is a little bitty m. So make sure you can differentiate. So molarity is just equal to moles over liters. And the moles that we're going to be talking about are going to be for the solute. And the liters is going to be for the entire solution. And that's it. So first example. Here it asks, what is the molarity of a solution that has 25 grams of sodium chloride dissolved in enough water to make 500 milliliters of solution? So I know that my formula equals moles over liters. So I'm going to need moles on the top and liters on the bottom. Well, I'm given grams and milliliters. So the first thing I'm going to do is I'm going to start with my 25 grams, and it happens to be sodium chloride. And I know that I don't want it in grams. What can we convert to? Moles. So we get rid of our grams and go to moles. And we know that 1 mole for sodium chloride, that's 58.44 grams. You found that on your periodic table. So now we got rid of our grams. We need to divide it by liters. A couple different ways you can do this, however, whatever you think would be best. Some people like to just throw a 1 down here. If you wanted to put your liters or milliliters down there, you could have. You can just come over on this side if you want. If you would prefer, it doesn't really matter as long as you get it into the denominator. Okay, so here we have milliliters. Let's just throw a 1 on top to make everything look nice and pretty. Well, we don't want it as milliliters. We want it as liters. One of these big things, there's 1,000 of these little things. So when we see how everything cancels out, we're left with moles on top, liters on the bottom, which is exactly what we wanted. And I need to be able to calculate this, which it comes to, I'm going to do the calculator because we're kind of squished for time here. It comes to, how many sig figs would we do? 3. So 0.856, and you can answer that as moles per liter Or you could say 0.856, big capital M, molarity. So either one of those would work. Okay. Next example is very, very similar. Here we're still looking for molarity. We know it's going to be moles per liter. So if we're starting with grams of zinc nitrate, 35 grams of zinc nitrate. Knowing your nomenclature, how do you write zinc nitrate? Okay, NO3. And then 2. Okay. Okay, so let me add that up in my head really quickly. We have 189.4 grams for every 1 mole. So now we've got it as moles. So we need to divide by liters. You guys are welcome at this point. You can probably look at this. You're very bright people. You can look at that and probably just move that decimal. You don't have to show all of this work of your milliliters going to liters. If you prefer to, please do it. But if you want, you could just take this and say 0.50 liters. Also, if you'd prefer, if you're on a space-saving mission, feel free to even put it down here to say 0.750 liters. Doesn't matter if you put it off to the right, directly underneath, just as long as you put it in the denominator. So now your grams canceled, you're left with moles over liters, which is exactly what we wanted. So we are done because we've got the units that we want. When we calculate this, we get 0.246 molar solution. Moving on. So example 3. Here we're looking for grams of sodium chloride needed to prepare so many liters of a certain molarity solution. So I know my formula is moles over liters. What I want you to think about here is think just about dimensional analysis. In this case, we've got liters. Would you say that's 1 or 2 units? 1 unit, right? So we have 1 unit there, 2.5 liters. Over here, never in your dimensional analysis problems are you ever going to see a big capital M. It's never going to cancel out with anything. So instead, we have to take that big capital M and change it to moles per liter. So if you think about it in those terms, that's going to make the dimensional analysis a lot easier. There's 2 units. So the question is, do you start with 1 or 2 unit? And you guys know you always start with the 1 unit. So we're going to start with 2.50 liters of a solution. And we want to get rid of our liters. Where could we go to? What's always the answer? Where could you go to? Do we want to go to milliliters in this case? No. We're moles. We go to moles. So notice right here, this is where we've got that's going to come in handy. So what number goes with the moles? 1.34 goes with the moles. What number goes with liters? 1. So if we were to stop right now, we would have our answer as moles, and we don't want it as moles. We want to get to grams. So 1 mole of any substance is equal to its weight in grams, so we can say that's going to be 58.44 grams for sodium chloride. So everything canceled out nice and neatly, except that, which is exactly what we are looking for. So calculating away, we get 196 grams of sodium chloride. Now, let's say you're an algebra person and you really hate this dimensional analysis stuff. If you were to come down here and look at this formula and try and algebraically change that around to solve for, well, it's solving for grams, you would know that you're given molarity and you're given liters, so you would have to solve for moles. So if you change that around to solve for moles, what you're saying is that you're taking it and making it equal to molarity times liters. There's your molarity, There's your liters. All you're doing is multiplying those together. So it still works to do it algebraically as long as you show all of your units. That's exactly what we did. Okay. Next one's real similar, so we're going to go through this really quickly. We start off with volume and moles per liter. So let's go ahead and write down our 1 unit of volume. I'm going to put that down because it's less work, and we all like less work. So we start with our volume. We don't want liters. We can go to moles. We know that 2.5 goes with the moles, 1 goes with the liters. Now we have it as moles. We just have to take it and convert it to grams. 1.270, because what I did was I took this many milliliters. There's 1,000 milliliters in a liter, so we just converted that. Okay, so 1 mole of copper 1 sulfate. How would I write that? C. And sulfate's -2. SO4. Okay, Cu2. I don't know why I wrote it there. Okay, let me rewrite. Okay, grams of copper 2 sulfate. And when we add that up, we end up getting 223.16 grams. So, again, everything cancels except grams. And our final answer is 709 grams of Cu2SO4. Okay, last problem that we have. Notice that so far what we've done is we calculated molarity, we calculated mass, which means we calculated moles first. So now what we want to do is we want to solve for volume. And the way this one's phrased, it says what volume of water in liters must be added to so many grams of potassium silicate to form so many molar solution. Assume the volume of the potassium silicate is insignificant. It could have just as easily said, what is the volume of the solution that is created when 65.8 grams of potassium silicate form a 1.25 molar solution. So we're not thinking about the volume of our solute. So in this case, I know my formula is this. Just reminding myself of that we'll talk about here in a minute. We have molarity, which means moles per liter. You don't have to cross that out and write that each time, but I just want you to think about that that's not 1 unit, that's 2 units. And then we also have grams. So grams is 1 unit. So let's start with that one. And it's potassium silicate plus 1 minus 2. So we need to, what are we going to convert to first? Moles. So we get rid of our grams, go to our moles. 1 mole is equal to 154.29. So now we have it as moles of potassium silicate. So we come over here, and we don't want it as moles. What do we want it as? Liters. Yeah. So that's when you look up here, and you have to, what number goes with the liters? 1. What number goes with the moles? 1.25. So what you ended up doing was you flipped that. In other words, if you change this around algebraically, you would be saying liters equals, what does it equal? Good. Moles over molarity. That's exactly what you did. You took your moles and you divided it by your molarity. That was flipped. These units were flipped. So it's the same thing. It works out the same way, but dimensional analysis is a way of ensuring that you don't make some goofy little multiplying instead of dividing type of error. It keeps your units, track of your units. So we know everything canceled but liters. In the final answer, 0.341 liters. Ta-da! We are done for the semester.